thanks so much for the invitation, Jan. It's really quite an honor to be able to talk about this work to this audience, which has a lot of the current and future leaders in this field, people who have thought about these issues for a long time. So I'm calling this paper Causal Identification with Subjective Outcomes. It's really sort of an econometrics paper, an econometric theory paper, and so there's not going to be any data or empirical results today. There will be a lot of sort of notation, and hopefully I can avoid sort of drowning us in too many equations. I think only having 20 minutes will help. So what I'm after with this project is I'm thinking about survey questions like those that we often use in well-being research that ask individuals to pick from a set of ordered responses, where the sort of definition of the categories, or sort of ordered categories, where the kind of definitions of the categories are sort of left somewhat up to the individual. So at the bottom of the slide here, I've shown some additional examples, but what I'm going to focus on as sort of the running example here is something like the Cantrell ladder of life question, or some other kind of life satisfaction question. Recall with the Cantrell ladder, respondents are asked to choose an integer between 0 and 10, where 0 represents the worst possible life, while 10 represents the best possible life. And we're usually interested in thinking about these responses, call them R, as a function of sort of as an outcome, given some explanatory variables, call them X, that we also observe in the survey. And if one is interested in modeling the responses themselves, then it's quite natural to approach this with a sort of regression kind of framework. But often we're interested, it might be sort of appealing to think of these responses as sort of only instrumentally useful to try as a window to sort of get to learn something about individuals' sort of underlying latent life satisfaction, which we can't directly observe. If we go this sort of route, this brings us to the idea of what this literature following Andrew Oswald has called the reporting function. The idea that there is some way that individuals map their underlying true life satisfaction, which we might think of as a continuous variable, into one of the available categories that is offered by the particular survey question we're offering them, right? And, if the sort of definition of the categories is sort of subjective, what is an 8 out of 10 life? What is a 9 out of 10 life? We might expect these reporting functions to vary by individual. And this is sort of the starting point of this project is I'm going to think about the linear, the sort of regression approach to analyzing these life satisfaction scales as an outcome variable without assuming that these reporting functions are the same for everybody. And beyond that, I also want to relax another assumption, which we might think of as sort of being implicit in the use of regression analysis, which is the idea of linearity. The idea that the difference between a 2 out of 3 or sort of a 2 out of 10 life and a 3 out of 10 life is in some way sort of quantitatively equivalent to the difference between say a 3 out of 10 life and a 4 out of 10 life. If that doesn't hold, that would not hold in a setting where individual reporting functions are not linear functions. Now, I should mention there is another sort of kind of approach to analyzing these kinds of variables as outcome variables that's common in practice, and that's to estimate a sort of parametric ordered response model, like an ordered probit or an ordered logit model. This, you might think of this as relaxing linearity while maintaining interpersonal comparability. This is the idea that if I say I have a higher life status, if I give a 9 and you give an 8, then we can infer that my underlying life satisfaction is indeed higher than yours. So the ordered probit approach might maintain interpersonal comparability while relaxing linearity. but it comes at a cost of making additional assumptions about, say, distributional, parametric distributional assumptions. And so what I want to do with this project is think about, suppose we go the regression route, and we're going to relax both interpersonal comparability and linearity, and ask, sort of, does regression tell me something that is sort of meaningful and interesting without making these strong assumptions? And in particular, I want to sort of think about this question when the sort of object of interest is the causal effect of some explanatory variables x on y, or sorry, x on responses r. So, ex ante, if we start to allow individuals to have their own reporting functions, then it might seem that we've made the problem of causal inference, that much harder, right? Because it could be that variation in reporting functions confounds the sort of causal relationship of interest. For example, think about we were interested in, say, the impact of wealth on life satisfaction. Suppose we observe that life satisfaction and wealth are positively correlated. Not only do we have the sort of traditional problem of selection bias, the idea that individuals that are wealthier may be happier, not because they're wealthier, but because their life is going well in other ways. But it seems we've added now a second potential problem, which is perhaps wealthier individuals have sort of systematically more optimistic reporting functions. Maybe they have a lower threshold at which they would say they are satisfied with their life as compared to a less wealthy person. However, in a lot of sort of modern empirical work, in the tradition of causal inference, we are sort of focused on finding natural experiments, where we have some variation in an explanatory variable of interest, x, that we think is sort of random or as good as random. And this might offer us sort of a path forward, even though we seem to have made our problem harder by allowing reporting function heterogeneity. The basic insight here is going to be the idea that x is not only statistically independent of potential outcomes in the language of causal inference, solving the selection problem, but it may also be sort of unrelated to heterogeneity in reporting functions, right? And I think you've seen this idea mentioned before, and I'm going to try to sort of formalize this by assuming that x is statistically independent of sort of two things. Okay, so just as an example here, a literature has looked at using lottery wins as a way to assess the effects of wealth on life satisfaction. Here's a fairly recent paper that looks at long run effects. Not only are people who won the lottery sort of similar to those who played the lottery but did not win in terms of their potential outcomes, that is how happy they would be with and without the win, but we might be willing to think that on average, sort of the distribution of reporting functions in both of those groups, treatment and control, might be fairly balanced, at least ex ante before the lottery win. So if winning the lottery changes your reporting function, there's nothing that in what I'm going to say that's going to allow you to deal with that problem. But I think that's an interesting avenue where there might be some potential progress to be made as well. So let me give you sort of the basic notation of how I'm going to set things up here, which is I'm going to imagine that the researcher observes two things, responses r and these explanatory variables x. And we're going to imagine that the responses here are generated from some well-defined latent variable, which we'll call h, for happiness, which reflects their sort of true, unobserved, to the econometrician, unobserved value of life satisfaction. And I'm going to allow each individual to map h into r with a function r sub I, which is specific to them. So that's their individual reporting function. Now, just as sort of another way of denoting the same thing, This second equality here on the right rewrites this as sort of a common function R that takes as argument not only H, but also sort of a vector of parameters which characterize the heterogeneity in reporting functions between different individuals, right? So you can think of V as sort of a representation of that individual's reporting function. And I'm not going to assume that V is a scalar or anything like that. It could be any finite dimensional vector. And so this is really just a matter of notation. It's compatible with every individual having their own person-specific reporting function. Now, in the second line here, I'm going to think of sort of true happiness or life satisfaction. I'm going to use these words interchangeably, sort of sloppily. We're going to think of this as being generated from explanatory variables by a function h, which again is specific to a given individual. And in the sort of language of causal inference, you can think of this hi function as denoting the potential outcomes of individualized happiness with respect to counterfactual values that the x variables might take, right? And again, I'm going to do the same sort of trick where I rewrite this as h of not only x, but a vector, a sort of a parameter which characterizes heterogeneity in potential outcomes, ui. So you could think, ui as a simple example might be just like, you might have a sort of genetic predisposition towards being having high life satisfaction, and any other thing that's going to sort of factor into your life satisfaction in addition to the variables x. Okay. So again, no restriction on the dimensionality or anything of u. Everybody can have their own potential outcome function here. And so in particular, the effect of some x variable on me might be different from the effect of that same x variable on you. We can have heterogeneous causal effects. Now, the sort of function that we'd like to learn about is this h function, right? This describes the causal relationships of interest. It tells us how potential outcome, how sort of counterfactual happiness levels vary with possible values that the x variables might take. But of course, the challenge here is that we don't observe the random variable h, right? This is latent. All we do observe are the sort of actual responses people give and the observable x for them. Okay? And again, x here can be a vector. It doesn't have to be just one thing. And in fact, when I get to sort of an overview of the results in a couple minutes, I'm going to emphasize a setting where we have at least two x variables to compare to one another. So just to sort of show you how this sort of notation nests kind of familiar models like the ordered probit. In the ordered probit model, everybody has the same reporting function, which you can think of as taking the following form. I'll choose category R. If and only if my happiness lies between, some threshold tau of R and the next lowest threshold, call it tau R minus 1. But in addition to that, the ordered probit model makes some strong assumptions about this relationship here. It assumes that it's sort of additively separable and linear in all the x's, and with a scalar error here that has this assumed to have a normal distribution. So I'm going to try to ask, what can we learn about h without making these sort of additional assumptions here? And in particular, I'm going to think about this from the perspective of running a regression. What I am going to assume are two sort of main identifying assumptions. So first, I'm just going to assume that the reporting functions are weakly increasing. So nobody would give you a lower number if their happiness went up, right? I'm just going to assume that away. This, I think it's worth emphasizing, is compatible with all sorts of interesting sort of utility maximizing behavior you might think individuals have. Maybe I don't want to tell you that I have a 2 out of 10, and so I shade my responses away from how I actually feel towards some intrinsic preferences I have over the categories. That's compatible with this assumption, and I discussed that a little bit in the paper. Happy to talk about it in the Q&A. But if we assume that these response functions are increasing, then with this integer response scale, like suppose it's just 0, 1, 2, the individual reporting functions are going to look like, staircases, right? There'll be some threshold at which a given individual would move from, say, category 0 to category 1. There'll be another threshold where they would move from category 1 to category 2. But with individuals having their own reporting functions, this individual over here on the right might have a different reporting function from the individual on the left. In particular, the one on the right is sort of more optimistic. The thresholds are lower for them. So they're going to, for some values of happiness, say that they give a higher response than the person on the left would. Okay. The second assumption I'm going to make is the one that I described in words before, which is that, the X variables are statistically independent, both of my heterogeneity and potential outcomes. That's, my natural experiment has solved the selection problem in causal inference. But in addition to that, I'm going to assume that X is also independent of the reporting functions, the heterogeneity and reporting functions. And in the paper, I do this sort of conditional on control variables. So maybe you observe other things in the data, you want to hold those fixed, and you think this assumption might only hold after conditioning, so a kind of conditional independence assumption. And the same sort of results are going to go through in that setup, which is, honestly, a lot more common that people have a kind of selection on observables kind of research design than a pure randomization like we have with the lottery. Okay, so here's kind of an overview of what I find. And I'm not going to go through everything in detail here. I think what I'll do is I'll give you an overview, and then I'll kind of drill down a bit on this first one to kind of give you a sense of sort of exactly what I see formally. The first thing I do is look at a continuous X variable. So suppose we've got something like income, and we're able to look at the derivative of the conditional expectation function of responses with respect to that X. This is what regression, aims to uncover. The first result is that this gives a sort of what you might call an unnormalized average of the derivative of individual potential outcome functions with respect to that X variable, where we're sort of averaging across different individuals, in particular, those individuals who are on the margin between adjacent response categories, which I think is sort of intuitive. I'll talk you through this result in a moment. Now, I say unnormalized here because the sort of overall weight given to different individuals' causal effects is not known. It's not going to add up to 1. It's not going to add up to something that we know. And so this leads to kind of a normalization issue if we want to sort of interpret this quantity, which is observable, in terms of these causal effects here. But the sort of, I think, pretty encouraging result here is that if you take two continuous X variables and take the ratio of the regression derivative with respect to the first and that of the second, that this ends up being quantitatively meaningful. So, just as an example, this paper by Lutmer, 2004, compares the effects of my own income on my life satisfaction to the effects of my neighbor's income on my life satisfaction. And here the kind of punchline is my neighbors have a negative effect on my life satisfaction, and the magnitude is actually about twice as big as that of my own income. Now, this result that I've just shown you here, I think, suggests that this ratio of -2 is actually informative even when these response functions vary by individual and we don't have linearity. So here's what I think is sort of a pretty encouraging result for applied work. Where things get a little bit less clear is when you start thinking about a discrete sort of explanatory variable. Suppose I have a binary treatment like winning the lottery. Here we're going to find there's sort of a similar expression for differences in the conditional expectation between two discrete points in terms of causal effects, but now the weights are going to be specific to a given treatment variable. And unfortunately, different treatment variables are going to have sort of a different total weight. And this means that when I take ratios, the weights aren't going to cancel out and as nicely. And in principle, these ratios could be misleading. So one thing I work on that I won't talk about in detail here is trying to figure out sort of how bad the problem can be. Can we construct some bounds on sort of how off these ratios might be? And I do have some analytical bounds that assume, if we assume linearity of individual reporting functions, but we still relax interpersonal comparability, I can get a bound that would suggest that if you were to compare, say, a discrete regressor or coefficient on a discrete regressor to the coefficient on a continuous one, that the magnitude of the discrete coefficient is going to tend to overstate relative to the continuous one, but by a factor that's not larger than 2. And in fact, under additional assumptions, is going to be a lot closer to 1. It depends on how many people sort of choose the extreme response values. Now, in simulations, I sort of assume a whole bunch of different distributions for underlying happiness. And I find that in practice, unless the causal effect of the discrete treatment is very large, like implausibly large, that in practice, these ratios are close to being sort of right. So happy to talk about that in more detail in the Q&A. There's some other extensions I'm also happy to talk to. I apologize for skipping all the literature review here in the interest of time, but another thing we might want to get into is sort of how my result here comports with this sort of well-known limitation, sort of no-go result by Bond and Lang, 2019. So Jan, if I could take just maybe 4 more minutes or so, let me just show you some detail about this first result, just to give you a sense of how my setup, the notation can be useful. So the basic result underlying things is what I give here. Here I'm considering the derivative of the conditional probability that an individual chooses a response that's less than or equal to a given value little r, and how that varies with a small change in x. And the result is that this is equal to minus an expectation, where inside that expectation, there's another expectation. The inner expectation is the sort of causal effect we're interested in, the derivative of the h function with respect to xj here. So xj can be just one component of my x vector. But the average is over individuals who are on the margin between two response categories. So let me give you a little more intuition visually for what this is saying. Imagine I'm just looking at the so I'm looking at the probability of giving a 1 response or lower. Oh, sorry, actually, let me go back one. Okay, suppose I'm looking at the conditional probability of giving a 0 response, how that changes with x, right? I take this derivative. It turns out what this gives me is, proportional first to the density of happiness at the margin between an individual's own threshold between the 0 and the 1 category. Now, of course, this depends on individual. This is why I'm averaging over response categories. So something I didn't mention here is that this outer expectation here, so this expectation is over individuals who are marginal between response categories, but having a given response function, reporting function. The outer expectation is over the different response functions that show up in the population. And this integral here is just another way of writing that outer expectation. Okay, so fixing a given reporting function, I'll have some density of individuals that are right there. Of course, in the background is some latent distribution that we don't know. And among those individuals that are right on the threshold, some of them might have causal effects that go in one direction, others might have causal effects that go in other directions. They might all have different magnitudes. We have heterogeneity in causal effects. That is what's being averaged over by this red or purple quantity here. And this is then multiplied by this density. Now, if I were to instead look at the conditional probability of having a 1 or lower response rather than a 0 or lower response, well, then that just focuses attention onto this next threshold. So here again, I'm averaging over all the response functions in the population, and then within each one, I'm getting an average causal effect among those individuals who are on the threshold between category 1 and 2, that is at this threshold for them. Now, what happens if I look at the conditional expectation? Well, here we can employ a little trick that relates the conditional expectation function to these conditional probability functions that holds if the responses are integers. So if the responses are 0 to 10 or 0 to 5 or 1 to 7 or something like that, then we can actually use that result from the last slide to show that the derivative of the conditional expectation function is going to be averaging over individuals at any of their categories. We're just going to sort of equally weighted sum over all of them. And so this hopefully gives us a more sort of representative picture of the sort of effect of X on H by sort of averaging over different points that may be sort of spread out in the distribution of latent happiness. So I know I'm out of time here, so let me just end by sort of pointing out how this ratio result emerges. So the result I showed you on the last slide, you can actually think of it as a generalization of the formula for marginal effects in an ordered probit. And we know in the ordered probit that the scale of the marginal effect is not identified without some sort of normalization. The way this manifests here is we don't know what these densities are as the researchers, so we don't know the overall sort of weight that these guys are being hit with when we average over them. But when we take the ratio of two continuous variables, we end up with two sort of nice convex combinations so that is well-defined averages of the causal effect of variable 1, x1 on happiness, where we're sort of averaging over all those individuals marginal between two response categories. And in the denominator, we have the same thing for another variable. And each of these can be thought of as sort of average causal effects. And if we're willing to make some additional assumptions, like that everybody has the same causal effect, or maybe a little bit stronger, a linear model for the sort of potential outcome function H, then we'll exactly learn the ratio of the effect of variable 1 on happiness to the magnitude of the effect of variable 2 on happiness. Okay, so let me stop there. We can go through some of this stuff more if anyone wants in the Q&A, but I'll just leave up this conclusion slide. And yeah, and thank you for your attention.
Len, brilliant. Thank you. Wow. And I think we still have a bit over, actually 22 minutes of time for Q&A.
Oh, great.